I'm Nick Baumann.
I'm Milani.
And our project is interferometric measurement of thin film induced stress.
So the piezo interferometer that we were using was the Zygo XPZ verifier. The source is a laser which goes through a spatial filter and a collimator to give us collimated and coherent light as our source. That then passes through a beam splitter, and after that there is a reference flat, and the reference flat is the back surface of a glass plate which we had mounted into the interferometer, and because the first surface has an AR coating on it to minimize the reflections. After that is an air gap, or the air wedge, which just has the index of whatever the air is, which is why this interferometer is very sensitive to environmental changes. If you blow into the interferometer chamber, you can see fringes shifting. And then after that is our test surface, which is the silicon wafers that we were mounting on there. It is then reflected back through the system. It is reflected into an imaging system.
This is the Stoney equation, which we use to calculate the stress induced in the substrate by the thin film. These are the values for our system: the Young's modulus of the substrate, the Poisson ratio of the substrate, the thickness of the substrate, and the thickness of the film. And here's a schematic of the substrate and the film. This is a schematic of the splitter deposition chamber. We have a target and a substrate with a large electric field in between them. The chamber itself is ultra-high vacuum, 10 to the minus 6 torr, and we inject a tiny bit of argon to induce a plasma. And that plasma rips off atoms from the target surface and deposits it onto the substrate.
So when the piezo interferometer is actually calculating the height error at each point on the test surface, what it's using is something like these equations, which come from Chapter 4 from Thomas Milster's graduate level course. And what the interferometer is doing, most likely using a piezoelectric device, is it'll move the reference flat by integer values of delta D. It effectively changed the optical path by lambda over 4. After taking multiple pictures, this equation is given the case where the camera will take 4 pictures of the intensity patterns on the fringes. It can solve for the height error, which is epsilon xy at a specific point, and the piezo interferometer will calculate the height error, and then it will give you a map of the test object.
Here we are sputtering the target material onto a sample so we can measure the deposition rate to calibrate our future depositions.
This is us using a profilometer to measure the deposition rate off our sample material that we deposited on. This is the Zygo XPZ interferometer that we are using to measure the stress in the silicon wafers, which, as you can see, Nick is mounting onto the mount.
After aligning the interferometer, we use the tip and tilt to get the center of the fringes into the center of the image like this. And after that, we'll be able to take the measurement of the sag in the wafer. So this was our first deposition from sputtering, and you can see we missed the center of the wafer by quite a bit. We were off center a little bit like this way, so you can see there's like a lack of film here, which makes the fringes sort of like shifted up and have a weird shape. Here's where we calculated the final stress value right here from our raw data here. These are the displacement values in terms of lambda, and we ended up with radius of curvature measurements here, which we then calculate up here. All right, here are the results from our interferometer measurements. You can see the change in height delta H on each wafer, the radius of curvature calculated from that, and the resulting stress in megapascals.